feel the vibe.
What's up, guys? Welcome back to another Algebra 2 instructional lesson here with Mr. Gaines as we continue our exploration of radical expressions, dealing with what's going to eventually get us into root functions. If you guys haven't watched the last video on simplifying radical expressions, make sure you do, and go ahead and like that video, give it a big thumbs up, and subscribe so we can keep this great math content coming your way. In all seriousness, let's get down to the math. Today we're going to be focusing on the operations with radical expressions. So what I've got up here on the screen for you are some properties, and it may look a little bit complicated, but as we start to break this down, you're going to see some rules that are going to help us out. So we're going to go under the assumption that what we're dealing with here are real numbers or real valued expressions. I'm not working with any imaginary numbers right now. The product rule tells us that if we have two roots that are identical in their power, so notice that little number, this is the 8th root, a root of x, and the a root of y. If the roots are identical, we can multiply together the radicands. Also, if it'll help us to simplify, which we have been doing this in the past, we can take two factors and split them apart into two roots, which that's what allows us really to simplify. So we've been working with that. The quotient rule we've also been working with, but not as in depth as we're going to see in this lesson. So the quotient rule follows the same kind of pattern. If we have two roots that are identical, again, their powers they are the same, then we can divide the radicands, the numbers on the inside. It's also may be helpful if we are giving a fraction inside of a root, we can split that up into two roots. Now the arithmetic property is the one that looks really complicated here, but you guys are probably already intuitively going to follow through on this one. So we have a bunch of different terms here. We have r times a to the x, or the 8th root of x, plus b, the bth root of x, plus the 8th root of y, plus s times the 8th root of x. Right here we see that we're adding terms. If you remember back to Algebra 1, you talked about when adding terms, you can only add the common expressions. And the same thing happens with roots. So if we look through here, we have some roots that have the same power. So the odd one out is the bth root of x, but here we have the 8th root of x, the 8th root of y, and the 8th root of x again. The only ones we can add together is if they have a common power and the radicand is the same. So the 8th root of y cannot be added to the ones that have x on the inside. If they are the same, we add their numbers out in front. So you've done this before with variables. Let's say you had 2x plus 3x, you would say this is 2 plus 3x, or 5x. The same thing happens with roots. So if I have 2 root x plus 3 root x, I would take 2 plus 3 root x to get 5 root x. So you guys can probably follow through that pretty intuitively, but we want to make sure we have those properties down as a basis for us to continue our work with simplifying expressions. So some of these problems here in number 2 and then on to number 3 and 4 are going to require those properties. Some are not. Let's go ahead and take a look at problem 2A, B, and C. Let's see if at this point you can pause the video right now and complete 2A, B, and C. Okay, let's go ahead and take a look at our answers. Hopefully you got some answers down for those at this point. These are problems similar to what we saw in number 1. So in problem 2A, all we need to do is find the square root of 18. And so you can realize that maybe 18 is not a perfect square. If you need to define that in the calculator, you could go under y equals and look for x to the 2nd power and see if that is in the y column. 18 is not, but 9 is, and 9 is a factor of 18. So I can break 18 down into 9 times 2. 9 could be rewritten as 3 squared, so this becomes 3 root 2. Hopefully everybody was able to get that one. B follows a similar concept, but here now we're dealing with a cubed root. So we have the cubed root of 125x to the 4th. Well, if I take a look at what perfect cubes are, we may see that 125 is a perfect cube. So 125 could be written as 5 cubed, and then we could write x to the fourth as x cubed times x. Then we could simplify that 5 cubed and that x cubed. So we have 5 times the 5 that's already there on the outside, and then x come to the outside with the cubed root of x remains inside the radicand. Both of these are definitely review from what we did previously. Now C gets a little bit more complicated. In C, we actually have to deal with a fraction here. So what you can do is you notice that in the numerator the fraction is being added. The way that it's listed right now, we can't add these two together because they're not like terms. One has a square root, one does not. So what I'm going to go ahead and do is split this into two fractions. So negative 4 over 2, which will simplify it a little bit, and square root 20 over 2. I'm going to go ahead and simplify square root 20 as well into 4 times 5. And we know we can take the square root of 4. The square root of 4 would be 2, and I'd have 2 root 5 over 2. This would simplify further. Negative 4 over 2 is negative 2. The 2 and the 2 in this fraction, in the second fraction of our second term, would cancel out and would leave us with root 5. So these are all questions that up to this point we should be able to do. Let's go ahead and take a look at D. D is where our properties start to come in handy. So in 2D, we need to simplify this expression where we have the multiplication of a number to two cubed roots. Well, notice that both of these are cubed roots. So what I can do is I can multiply what's on the inside, the radicands. So I can take the 16 times 4, because those are both integers, and multiply those together. I'm not going to do anything to the 1.2 right now, so I'm going to leave this as 1.2. And then now I'm going to create one cubed root where I take 16 times 4, which is 64. And then n to the fourth times n to the fifth. Let's remember back to our Algebra 1 skills. When we take two variables and multiply them together, we add their exponents. So this would be n to the ninth. Now, again, I'm looking for a cubed root, so I need powers of 3. Numbers that can be taken to the third power. And I'll notice that 64 is the same as 4 to the third power. So I'm going to go ahead and skip kind of one of our steps that we've been writing down. If you need to write 64 as 4 to the third, you can. But what I realize is that if I cube root 64, that answer is going to be 4. So I'm going to have 1.2 times 4. And the cubed root of n to the ninth, notice that this exponent 9 is triple what's required for a cubed root. So n cubed is going to come out. Then I can simplify a little bit further. 4 times 1.2 would be 4.8. So this answer is 4.8 n cubed. Okay. Now you could have simplified those roots individually first and then multiplied their answers together. But then you'd have to find that you were going to simplify a little bit further. So sometimes it's easier to combine the roots and then simplify. Let's take a look at E. E is one of those cases. So using the quotient rule, because these are both square roots, I can simplify them individually if I wanted to, or I can combine them into a single square root. So this is using the quotient rule. Let me put that quotient rule up on the screen. If we were to start here with 2 square roots, we can combine them into a single square root with one fraction. So I'm going to do that. And what we'll notice is when we complete this step is that now there's some simplifying that we can do in the fraction. We can take 18 divided by 2, which would be 9. And then we can take a to the fifth divided by a to the fourth. Remember, if you divide variables, you subtract their exponents. So this would end up being a to the fourth. So a to the fifth divided by a to the first power is the same as a to the 5 minus 1 power, which would be 4. Now what that allows us to do is to simplify this expression. So we should know that the square root of 9 is 3 squared, so the square root of 9 would just be 3. And if I square root a to the fourth, the 4 is double the power that's required for simplification. So I would have 3 a squared. So in this case, it's easier to combine those two different roots into a single root. In f, we're looking for the cubed root. Now again, I have on the screen here on my calculator the perfect cubes. Sorry, under the table, under the y. And what I'll notice is that if I want to simplify this, initially, if I want to simplify this fraction does not simplify. So previously we combined two roots into one so that we could simplify the fraction. But if I wanted to simplify 8 over 125, or sorry, let me try that again, 81 over 125, it gives me a decimal here in my calculator. If I put it in a fraction, it's still just 81 over 125. It doesn't simplify. So in this case, if I take a look at my perfect cubes, I'll notice that in the table, if I can get to the table, there we go, 125 is listed on the table. 81 is not listed on the table, but a factor of 81, 27, is. So this one, it actually might be easier for us. We can't simplify the way that it's written, but if we split it up into two cubed groups, now we can simplify, because 25, again, 125 can be rewritten as 5 cubed. And 81, I'll go ahead and replace this right now. 81 can be rewritten as 27 times 3. Well, the reason we write it as 27 times 3 is because 27 is just 3 cubed. So this is the same as 3 cubed times 3, or the cubed root of 3 times 3, over the cubed root of 5 cubed times x cubed. There, well, as I simplify in my numerator, I can simplify the 3 cubed to give me 3, and then I'd have a cubed root of 3 left over. In the denominator, I can simplify to give me 5 and x. So my answer would end up being 3 cubed root of 3 over 5x. So this one, in E and F, we see two different uses of the quotient property. In E, we used it to combine the fraction. In F, we used it to split the fraction apart. And in both cases, we were able to simplify. So we want to use that property strategically. Let's continue with some examples here as we take a look at G. Go ahead and pause the video and see if you can complete G and H. I'm going to go ahead and take I and J out of here. We'll talk about those at a later time, but see if you can complete G and H. Hopefully you guys got a chance to do both of those. In G, we may notice that we're looking for square roots here. So if I wanted to rewrite as factors here, I might rewrite this as 6 squared. I'll leave p to the 4th because that is a multiple of 2, and rewrite q to the 5th as q to the 4th times q. So 6 squared, the square root of 6 squared would just be 6. Square root of p to the 4th, this is as if we have the power of 2 with the root, so that's double the requirement to simplify. So this would be p squared on the outside, as well as q squared on the outside. And then I'd have the remainder of a square root 2, not necessarily a remainder, but I would have a square root q that is still there unsimplified. In V, we have a similar thought process. Sorry, in H, we're dealing with V's. We have a similar thought process. So V, then cubed root of V to the 4th, which we can split V to the 4th into V cubed, in V. So I would eventually get on the outside V times V, with a cubed root v left over, because I can simplify that first piece. And v times v is now v squared, and then cubed root of v. So some of these, we don't really need the properties that we had given to us at the beginning of right before problem 2. We can simplify those still using our techniques previously. So we want to be able to identify when to use properties and when we don't need to use properties. Now let's take a look at problem 3. So in problem 3a, sorry, part of this is cut off. Let me fix that. That looks better. So in problem 3, we want to complete the arithmetic operation. So here we do have to use the kind of arithmetic property that we discussed. So remember, basically what we're looking for is we can add and subtract. Subtraction is still considered the same property as division, or sorry, as addition. We can add or subtract if the radicand, the number inside the root, and the power of the root are exactly the same. So if I take a look at a, the way that it's written right now, I cannot add these. Reason being, they are both square roots, but the radicands are different. However, I may notice that I can simplify these radicands. So I can rewrite the square root of 45 into the square root of 9 times 5. I can rewrite the square root of 20 into the square root of 4 times 5. The reason that I want to rewrite those as those factors, because 9 you can square root. So again, if you needed that list, we would hit y equals, type in x squared, and then in the table and under the y column we see all the perfect squares. So 9 would be a factor of 45. 4 would be a factor of 20. We want to make sure we factor those, and then we can simplify. So this would give me 3 root 5. The square root of 4 is 2. So if I have a 2 coming to the outside, this would be 2 times 2, which is 4 root 5. Now when I take a look at these square roots, they are exactly the same. They're both square roots. They both have the same radicand, so I can add the numbers on the outsides, the coefficients. So 3 plus 4 would be 7. So my final answer would be 7 root 5. So we have to make sure that the root is the same type, they have the same power, and the radicand, the value on the inside, is the same. Let's take a look at B. In B, we can again take a look at these and see they're both cubed roots, but the radicands are not the same. So I need to simplify these cubed roots first if I can, and then maybe the radicands would be the same. So 16 is not a perfect cube, but 8 goes into 8 16, and 8 is. I'm going to split x to the 5th into x cubed and x squared. And then I'd have minus x cubed root of 54 is not on the list of perfect cubes, but 27 is. And 27 times 2 is 54. And then I'm going to leave x squared as it is. So I can simplify these pieces. So the cubed root of 8, if we want to use the calculator in the table, we can. The cubed root of 8 would be 2, because I set this up to find those cubes and cubed roots. The cubed root of x cubed we know would just be x. And then I'd have the cubed root of x squared. The cubed root of 27, so we're looking for the cubed root of 27, would be 3. So I'd have 3x cubed root of 2x squared, sorry. I forgot a 2 in my last radicand. So I did bring a 2 out, I did bring an x out, but I forgot to leave the 2x squared back in there. So again, this one would be 3 cubed root of 2x squared. Now we notice that they are both cubed roots, and both the radicands, the inside pieces and the inside expressions, are the same. So I can subtract the coefficients. So 2x minus 3x gives me negative x, and then the cubed root of 2x squared. Finally, on this problem in C, here we have some multiplication in combination with what we're doing. So if you think order of operations to simplify PEMDAS, parentheses, exponents, multiplication and division, then addition and subtraction, we might see that there are parentheses, so we want to simplify inside the parentheses first. But if we think about subtraction here, we cannot. We have the square root of 6 and the square root of 3, so the radicands are different. So let's go ahead and let's take a look at the multiplication of this. We can do the operation of distribution. We can multiply the 5 root 3 to both things. So 5 root 3 times root 6. Now here's our multiplication property for roots. They're both square roots, so I can multiply the numbers on the insides to each other. So the 5 is left unchanged. Root 3 times root 6 would be root 18. As I distribute the 5 root 3 to the 4 root 3, I would do 5 times 4, which is 20, and root 3 times root 3 would be root 9. And now I can simplify. So 5 root 18. 18 is not a perfect square, but it breaks into 9 and 2. And 9 is a perfect square. So the square root of 9 is 3. If I have a 5 on the outside already, I take 3 times 5 to give me 15. And I'm left with square root 2. In the second term, I would take the square root of 9, which is 3. Take that 3 times the 20 that's already there, and that would give me 60. I cannot combine the 60 and the 15 because one has a square root and one does not. So here we see a little bit of order of operations. We see a little distribution. We see our multiplication property for radical expressions. We see our product rule for radical expressions, and we see our arithmetic property for radical expressions. So we're combining a lot of ideas there. Let's go ahead and take a look at D, which expands on this a little further. You see two binomials that include radicals that are multiplied to one another. So as we would with regular variable expressions, so you guys have seen a lot of like x plus 3 times x minus 2, and you'd go through here and you distribute. We're going to do the same thing with these radical expressions if we cannot simplify in the parentheses. In this case, we cannot. I cannot add 2 root 2 to 6 root 3. I cannot add 3 root 10 to root 15, and I cannot simplify those because none of those are perfect squares, and none of those have factors that are perfect squares. So let's distribute here. So I'm going to take 2 root 2 times 3 root 10. 2 times 2 is 6. Root 2 times root 10 is root 20. Then I'm going to take 2 root 2 times root 15. So the 2 would remain on the outside. Root 2 times root 15 is root 30. I distribute the 6 root 3. So 6 times 3 is 18. Root 3 times root 10 would be root 30. Then I distribute 6 root 3 to root 15. So 6 root 3 times root 15 would be 6 root 45. Now that I've done all of this distribution like we would with, let's see if I can move this here, like we would with variable expressions, we want to simplify these, combine like terms if we can, and simplify those that we can't. So I'm going to take a look at this 6 root 20. There's no like terms, but root 20 can be simplified. I can rewrite root 20 as root 4 times 5. In my 2 root 30 and 18 root 30, I can combine those to get 20 roots of 30, adding their coefficients. And my root 45 can be broken down. There's no like term there, but it can be broken down into 9 times 5. Now I do want to simplify a little bit further if I can here. Square root of 4 is 2, so 2 times 6 is 12. I have 12 root 5 to start with. 20 root 30. Root 30 30's factors are 1, 30, 2, 15, and 5 and 6, and 3 and 10. None of those can be square rooted. So root 30 is as simplified of an expression as that can get. And then I have root 9 that simplifies to 3 times the 6 that's already out there, 18 roots of 5. Finally, I may notice here in the first term I have 12 root 5, and now I have 18 root 5 as the last term, so I can add their coefficients and end up with 30 roots of 5, and still plus 20 root 30. So there's a little bit of work here that we have to do as we distribute. Then we want to simplify using our ability to simplify radicals, and then combine the like terms. Taking a look at C, if you look at C, C looks a very similar problem, but it's actually a considerable amount shorter because what we may notice here is that these are two conjugates. So remember, we have a shortcut for multiplying conjugates. When you multiply conjugates, you take the difference of the two squares. So what I can do here is I can square the first term, x, then subtract the square of the second term, the square of the square root of 7. This simplifies nicely, so x squared minus 7 would be our final answer there. So you can distribute through that if you need to, but this is actually a problem we've probably seen before. You don't necessarily have to distribute there. We can use the sum of two squares, the difference of two squares property that we talked about earlier this year. For F, remember that to square something, now this people get hung up on this one a lot. To square something means to multiply it by itself. So what you could do is you could write this as 3 minus root 2 times 3 minus root 2 and distribute. But we also have that property for that identity for when you square a binomial. The square of a binomial would be the square of the first term, so 3 squared, plus double the product of both terms, 3 times a negative, sorry, and let me put this in parentheses here, a negative root 2, because that sign does go with the root 2, plus the last term squared. So negative root 2 squared. So if I simplify here, this gives me 9 plus negative, sorry, let's make this 9 minus, as that negative multiplies to the 2 and the 3. So 9 minus negative 6 roots of 2. And then plus, as when you square a negative, that becomes positive. Root 2 squared would just be 2. And now I can combine my 9 and 2 to get 11 minus 6 roots of 2. So if you have to distribute, you absolutely can do that. But if you do remember your properties and identities that we worked on earlier this year, that can save you some time. The final examples that we are going to work with deal with division and simplifying radicals. So when we take a look at fractions or rational expressions, to be able to compare them to one another, we need a common denominator. So a skill that we're going to need, you're going to need in the future as you get a little bit further beyond Algebra 2, is what we call rationalizing the denominator, to be able to compare fractions to one another. Rationalizing the denominator means we need a rational number in the denominator, meaning no radicals. So if I take a look at 4, it says to write each of the following in simplest radical form, basically rationalize the denominator. I need to get rid of root 3 in A. Now remember, this goes back to our properties in simplifying. If I were to wanted to simplify anything of the nth power, if I had a term on the inside, it would need the same exponent. So essentially what I'm looking at here is the square root means we have a power of 2 for that radical expression. So I need my 3 here to have a power of 2 as well. So what I can do is I can come up with something to multiply to root 3 to give it a power of 2, which would be root 3. So I'm just going to simplify the denominator for right now. If I multiply this by root 3, I would have 5 and then root 3 squared, essentially. And we know that that will simplify. But if I want to avoid changing my fraction, I need to make sure I multiply both things, the numerator and the denominator, by the same expression. That would be essentially multiplying it by 1. So what this allows me to do now is take the square root of 3 squared, which is just 3. And so this would turn into 5 times 3 in the denominator, which is 15. So this is an equivalent expression, but it's a rationalized denominator expression of what they gave us originally. Taking a look at B, this concept carries over to B. Now, instead of having a square root, we have a cubed root in the denominator. So what I'm focused on is getting the cubed root out of the denominator. So I need to multiply this x into something that will allow it to be simplified. Currently, it's an x to the first power. Well, if I'm dealing with a cubed root, I need x to the third power. To get x to the third power, I need to multiply in x squared. And that does have to be the cubed root of x squared so that I can combine those using my product property. If I multiply the numerator or denominator by an expression, I need to multiply the numerator by the same expression to avoid changing the fraction. So that negative 7 is going to remain. Then I'm going to have the cubed root of x squared now also in the numerator. And then the denominator, the cubed root of x times the cubed root of x squared, because they're both cubed roots, I can multiply their radicands, would be the cubed root of x cubed, which this simplifies to just x. So my final response here would be negative 7 times the cubed root of x squared over x. Let's go ahead and take a look at C. In C, before I even worry about rationalizing the denominator, I want to simplify the expression. So currently I have one fraction that I can break apart into two fractions, the cubed root of 3 over the cubed root of 4a to the fourth. Well, if I'm looking for perfect cubes, I have that list right here. 4 is not on that list, and no factor of 4 is on that list. So I cannot simplify the cubed root of 4, but I'm going to go ahead and break apart a to the fourth into a cubed times a. So what this leaves me now is a numerator of the cubed root of 3 and a denominator of a, because this one simplifies, times the cubed root of 4a. So this is not going to simplify for me the way that it's written because I have that cubed root in the denominator, so I need to get rid of it. Now I'm going to go ahead and break down 4 into, I'm going to call 4 2 squared. Now I could leave this as 4, but I'm going to rewrite it as 2 squared because that's going to allow me to simplify a little bit easier. So if I have a 2 squared, let's focus on that, and I need to get that out of the radical, or the root. I need that to be a 2 cubed. So if it's already 2 squared, I need to multiply by 2. The other way you could look at this is I could take a look at this and see that it's 4, and go over here to my calculator and say, okay, these are my perfect cubes. What can I multiply to 4 to turn it into one of these numbers? Well, I can multiply 4 by 2 to make it an 8, which then could be simplified. Okay, so you could look at it as a 2 squared or a 4. Now the a, there's only one way to look at the a. It's just a. And to simplify a, I'm going to need a cubed. So I need to multiply by a squared to turn a into a cubed. If I multiply something on the numerator in the denominator, I need to multiply the same thing in the numerator. So in the numerator, I have cubed roots that I can combine, 6a squared inside of a cubed root. In the denominator, I have cubed roots that I can combine. 8 is 4 times 2, and a times a squared would be a cubed. Then I can simplify this root in the denominator. So the numerator remains the same, cubed root of a squared, over the cubed root of 8 would be 2. The cubed root of a cubed would be a. I already have an a out there, so a squared. Okay. So this is kind of a complicated system here. It takes us a little bit of work, but the goal is to, again, make sure that if we want to simplify and get the radical out of the denominator, we need the root, or sorry, the power inside the root to match the power of the root. The last problem that we have here is 4D. In 4D, we need to rationalize, or sorry, 4D and E, we have two problems. We need to rationalize the denominator with these. Now, this is a little bit different. What you may look at this and you may say, okay, I've got a square root of 11. If I want to get rid of a square root of 11, I need to multiply by a square root of 11. But what that would do is turn this into 3 roots of 11 plus root 121, which would be 11. So really it doesn't simplify or rationalize the denominator. It just moves your square root around. So instead, we're going to go back to a topic that we talked about earlier this year. We, at one point this year, dealt with simplifying, let's say, 2 plus I in the denominator. And if you remember, we said that we were going to multiply by the conjugate, because when you multiply by the conjugate, you can use the difference of 2 squares, and then your imaginary unit became a real number. Okay, so that same concept actually is going to happen here. It's not going to work with imaginary numbers, but conjugates can be used to simplify expressions. So notice back on problem E, where the roots were, root 7, that root went away. There was no square roots when we multiplied together those two conjugates. That's going to be true for any binomial. So if I ever have a binomial, and one of the terms has a root, if I want to get rid of that root, I can multiply by its conjugate. So the conjugate of 3 plus root 11 would be 3 minus root 11. I need to multiply both the numerator and the denominator by that number or expression. So that would be 24 as I distribute. 8 times 3 is 24. 8 times root 11 would be 8 root 11 in the numerator. In the denominator, it's the difference of the two squares. So 3 squared is 9. Root 11 squared is 11. I can simplify this further. 24 minus 8 root 11 over 9 minus 11 would be a negative 2, which I can simplify further. If I need to, I can split it into two fractions. Let's just make this plus negative 8 root 11 over negative 2. Splitting apart into two fractions, this would give me negative 12 plus 4 roots of 11. So I can use, when I have a binomial where one of the terms is a root, I can use its conjugate to rationalize the denominator. The same thing would happen with e. So take a look at e and see what you would multiply by to rationalize the denominator. If you said root 6 plus root 2, you'd be correct. So again, we've used the conjugate here. And I'll do the denominator first this time, because the conjugate would be the difference of the squares of each term. So the square of the root 6 would be 6, the difference. The square of root 2 would be 2. In the numerator, I'd have to do a little bit more work here, because both of these are binomials and they are not the difference of two squares. So I'd need to do some distribution here. So I'm going to take 2 times root 6, which would be 2 root 6. I'm going to take 2 times root 2, which would be 2 roots of 2. I'm going to take root 3 times root 6, which would be root 18. And then I'm going to take root 3 times root 2, which would be root 6. Now I want to simplify. In the numerator, I may notice I have a 2 root 6 here and a root 6 there. They're being added together. That would give me 3 roots of 6. That 2 root 2 does not have a common term. Neither does the root 18, but the root 18 can be broken down into 9 times 2. In the denominator, I have 6 minus 2, which is 4. Simplifying the numerator further, I have 3 roots of 6 plus 2 root 2. And root 9 times 2 would become 3 root 2. I can simplify just a little further here. I have 3 roots of 6 plus 2 root 2 plus 3 root 2, which would be 5 root 2. All of this would be over 4, which I could split into two fractions if I wanted to, but neither fraction would simplify, and so that could be our final answer. Okay, so rationalizing the denominator is a skill that we work on and we develop in Algebra 2. We don't use it a whole terribly lot, but you do need to be able to rationalize the denominator to compare maybe different sources of answers, as well as, in time, adding together different types of rational expressions. This is a good place to stop as we have finished the RF.1 notes. Thank you guys for tuning in. As always, we will reconvene shortly in class to go over questions and to begin some practice on these concepts as we prepare for our assessment. As always, again, guys, thank you for tuning in. Go ahead and smash that like button and subscribe if you have not, and have a wonderful day. I'll see you soon.